All right, so we're on the second video for chapter 1, and we're starting on section 1.4. Section 1.4 starts, it's a preview for chapters 5 and chapter 19. It's just a little preview of what we're going to talk about when we talk about energy. And so energy is simply the capacity to do work or transfer heat. We'll talk about this, like I said, in chapter 5 in a lot more detail. Work is energy transferred from when a force is exerted on an object and it causes displacement to that object. And then a force is just any push or pull on the object. And then here, heat is the energy used to cause the temperature of an object to increase. So, so we will talk about that in a lot more detail in chapter 5. I just introduced the topic here because it does talk about that, and it talks about kinetic energy and potential energy, and we're going to save that for chapter 5. So now let's look at section 1.5, and we'll look at the units of measurement that we like to use. In chemistry, we're going to use a combination of both the metric system and the international system of units. The international system, in French, it's the Système International, and so we call them SI units. And so we'll find that each unit has a different base and that we use an abbreviation for that base. So for example, mass, you probably know this already. The name of the unit is the kilogram. So a kilogram is our base unit for mass. The abbreviation that we use for the kilogram is kg. For length, we use a meter, and the abbreviation that we use for meter, of course, is a lowercase letter m. So that one here, metric and SI are exactly the same. For time, again, we like to use the second, and we'll abbreviate that with a lowercase letter s. For temperature, in the SI system, we use Kelvin. It's an absolute temperature, and we use the abbreviation uppercase letter K, and you'll notice that there's no degree symbol here. When we're using the degree Celsius in the metric system, it does have a degree symbol. For the amount of substance, this is a quantity that we'll be using quite a bit we'll use this quite a bit in chemistry, and it is the mole, and our abbreviation that we use for mole is just all lowercase MOL. MOL. We're already using M for meters, and we use MO for molybdenum, and so we're going to use MOL for mole. For electric current, we like to use the ampere, and our abbreviation for the ampere is the uppercase letter A. Finally, luminous intensity. This is not something that we'll be using in this class or the 1412 class, but it is a useful unit when you start talking about instrumentation, and that is the candela. The abbreviation for that is CD, lowercase letter CD. Now, the great part about this is with these 7 base units, we can come up with the units for any other measurement. If we want volume, it's going to be a length cubed, right? If we want speed, it's going to be a length divided by an amount of time. And so we can make any other measurement by having combinations of these units. When we're using the metric system and SI system, we use metric prefixes, and metric prefixes, you have been introduced to them before, and there is a list of them that is in your textbook, and I want you to know from billion down to billionth for this class and be able to do conversions for those. So from billion down to billionth. I'll start with quadrillion. You don't necessarily need to know this, but it is kind of interesting. So 10 to the 15, and the unit that we use for that is peta. Our prefix for that is peta, and the symbol is an uppercase letter P. For trillion, 10 to the 12, this is one that you see quite a bit in computer terminology, and that is the prefix tera, and we use the uppercase letter T to indicate tera. For billion, 10 to the 9, we use giga, and we use the uppercase letter G. For million, we'll use, which is 10 to the 6th, we will use mega and the uppercase letter M. For thousand, of course, you know this one, 10 to the 3 is kilo, lowercase letter K. When we get to less than 1, we'll get 1/10. We use deci, so lowercase letter D for deci. For 1/100th, we'll use centi. This should be things that you're quite familiar with. So centi. 1/1000th is milli. All right, 1/1,000,000th. Here we use micro, and we use the Greek symbol mu to indicate micro. For billionth, we'll use 10 to the negative 9, and we'll use the prefix nano, so lowercase letter n, nano. For trillionth, all right, so I want you to know billion through billionth. So trillionth is just extra if you want to know it. And for that, we use pico, lowercase letter p. And quadrillionth, we'll just kind of round it out so that it's parallel here, and we'll use femto and lowercase letter f. So like I said, I want you to be able to do conversions between different metric prefixes. We're going to do a little bit of practice, but I don't have any on my in-class assignment where we're doing these. So for doing prefix practice, we've got some units here, and I just want to put the unit in terms of what the base unit is. So for example, 1 centimeter, cm, well, centi means 10 to the negative 2, and so that's 1/100th of a meter. And of course, we could write that as 0.01 meters, and that would be our representation in the base unit. So let's look at a couple other of these. 1 km, well, K means kilo, which is 10 to the 3rd, so that's 1,000 meters. 1.21 GW, well, W is watts, and G is giga, and giga is 10 to the 9. All right, so 1.21 times 10 to the 9 watts. All right, 5 mJ, and for 5 mJ, M is mega, and J is joules, and so that would be 5 million joules, which is 5 times 10 to the 6 joules. 1 ml, and that's 1 milliliter. And so a milliliter, milli means 1/1000th, so that would be 0.001 liters. 15 dl, so a D is deci, and deci is 1/10, so 15 tenths of a liter would be 1.5 liters. 2 mu m, mu is micro, which means 10 to the negative 6, so we could simply write that as 2 times 10 to the negative 6. One cool thing about this is if you know what the prefix symbol means in terms of the number, like 10 to the 6 for micro, 10 to the negative 6 for micro, you can just replace that prefix with that scientific notation and put times 10 to the negative 6 there. I'll show you examples of that as we do that a little bit later. 3 ng, that's a nano. Nano is 10 to the negative 9, so we'll do 3 times 10 to the negative 9 grams. 1.01 times 10 to the 5th km. Well, K means kilo, so 10 to the 5th times, and kilo is 10 to the 3rd, so 10 to the 5th times 10 to the 3rd is 10 to the 8th. That would be 1.01 times 10 to the 8 meters. And then finally here we've got 2 ps, and P is pico. Pico is 10 to the negative 12, so we will write that as 2 times 10 to the negative 12 seconds. Not a long amount of time at all. All right, as I mentioned, I do expect you to know how to do conversions between one prefix and another prefix, and we're not going to spend class time on that, so if you are uncertain about it, then you probably want to practice, and you can either go to the Science Learning Center, and we've got online tutoring available, and so online tutoring, or you can check me at my office hours, and I'll be glad to help. All right, our next thing is going to be temperature measurements, and we've got 3 scales that are commonly used. There are some other scales that I'm not going to talk about, but 3 scales that are commonly used: the Kelvin scale, the Celsius scale, and the Fahrenheit scale. The most commonly used throughout the world is the Celsius scale. It is the metric scale, and it is what most of the world uses. In science, we use Celsius, but we often will need to convert into Kelvin, and there's an easy conversion, but Kelvin is our official SI unit of temperature. You'll see that a degree change in Celsius is equal to a 1 Kelvin change in temperature. So a degree in Celsius is a 1 Kelvin change as well. And so it makes the conversions for those really, really easily. What gets a little bit challenging is when we have the Fahrenheit scale, which is used in some remote parts of the world, like, the Cayman Islands, Belize. There's this little place in North America called the United States. Apparently, they still use it. Anyway, it is a non-science unit. It has its advantages and its disadvantages, but I will say that most of the world has converted over to metric and Celsius. Anyway, temperature is it is a measure of the average kinetic energy. If you're using the Kelvin scale, if you double the temperature in Kelvin, you double the energy. It's directly proportional, which that's kind of cool. Some simple conversions are, say, a Kelvin is equal to the temperature in Celsius plus 273.15. If you want to convert to Fahrenheit from Celsius, you use this formula, and from Fahrenheit to Celsius, then you'll use this formula. These two are the same formula. In case you're curious, that back of the periodic table, all right, here's that back of the periodic table. Here are the temperatures, and we've got those conversions right down there for your convenience. So you have this available to you on the test, so you will always have those conversion factors. You just need to make sure that you know how to use those in calculations. All right, so now for volume, our SI unit of volume is the cubic meter. And the problem with a cubic meter is huge. So 1 meter by 1 meter by 1 meter, that's a large volume. And so if you're talking about how much water did you drink today, you're not going to use cubic meters for your unit. You might use liters. And so liters is our metric unit. And fortunately, there's an easy conversion between cubic meters and liters. And that is that 1 cubic meter is equal to 1,000 liters. So 1 cubic meter is 1,000 liters. If you look, 1 cubic decimeter, a deci is 1/10. So if you have 1/10 of a meter by 1/10 of a meter by 1/10 of a meter box, so 1 decimeter cubed, that's equal to 1 liter. That's a useful conversion. And then 1 cubic centimeter is equal to 1 milliliter. And that's also a useful conversion. And just in case you're curious, yes, I've got those right here. I've got those conversions right there for your convenience. I also have some that are non-metric, like a gallon to liters and stuff like that. So you don't have to memorize that. It is easy to do. All right, so we've got different things that we can use for measuring volume. Graduated cylinders, we use this quite a bit in the lab. If you're doing synthesis, syringes are really nice because you can measure out volume very accurately and keep it from getting exposed to air. If you've got something that's sensitive to air or water, syringes are really nice. Burettes, we use these quite a bit for doing things like titrations, and we've got a titration lab this semester, and we will get that all set up. Let's see, pipettes. If you want to measure out and dispense, deliver a specific volume, pipettes are really handy. You draw the liquid up, there's a mark, you draw the bottom of that meniscus to the mark, and then you just let the liquid drain, and that will deliver a very accurate amount of liquid. And so pipettes are extremely handy. If you're trying to prepare a solution and you want to contain a certain volume, you can use a volumetric flask, and it will contain a particular. It also has a line, and the bottom of the meniscus lines up with that line. and you put whatever you want to dissolve in your solution, and then you dissolve it, and then you finally fill up with whatever your solvent is up to the line and make sure everything's mixed up, and you will get a very accurate way of measuring out a specific volume. So very convenient. Our next thing that we're going to be looking at is density. And with density, we're going to be looking at how we do the calculations, and we'll be looking at the measurement itself. It is a physical property and an intensive property. So you can measure density without changing the chemical. And since it's an intensive property as well, that means that it is independent of the amount of substance. All right, and the units are derived from mass and volume. And the most commonly used units are either grams per milliliter or grams per cubic centimeter. Those are going to be the same. But you'll also sometimes see kilograms per liter, and that's actually going to give you the same number, which is kind of cool. But there are many ways to do it. But grams per milliliter or grams per cubic centimeter are the most common ways. All right, so the units are derived from mass and volume. The most commonly used units are grams per milliliter or grams per cubic centimeter. Those end up being the same number. Our formula is that density is mass over volume. And then if we come over here, we'll get the density of some common substances. Water has a density of 1 gram per cubic centimeter or 1 gram per milliliter. We'll see things that are less dense than water, like balsa wood, for example, will float on water. Air is much less dense than water. If we come down here, these things are much more dense than water. They will sink in water. So we want to look at a density problem. And the density problem we're going to look at here, and then we'll look at one on our in-class assignment. We'll actually look at 2 on our in-class assignment. So here we've got a copper sample has a mass of 44.64 grams, volume of 4.98. What is the density? So, all right, this is the first math problem that we've done in this class. And the very first thing what I want you to do when you're doing a math problem is ask yourself the question, what are we looking for? So much about chemistry is word problems, and you have to be able to read it and figure out what is it that we're looking for. In this one, it's really easy. We're looking for density. We have a formula for density, and that formula is that the density is equal to the mass divided by the volume. Well, now we ask ourselves the question, do we have the mass and do we have the volume? Well, yeah, we have the mass and the volume. Mass was given here at 44.64 and the volume at 4.98 cubic centimeters. So now we just have to put those numbers into the calculation. So 44.64 divided by 4.98, and we will get 8.96 grams per cubic centimeter. And that gives us our density. We will talk about significant figures a little bit later in this chapter. So we will talk about significant figures a little bit later in this chapter. All right, so 8.96 grams. All right, so let's look at number 28. We're going to go over here to our in-class thing, and I've got my calculator right there. All right, so here we've got a cube of osmium metal, 1.500 centimeters on a side, has a mass of 76.31 grams at 25 degrees Celsius. What is the density? Well, our formula for density is equal to the mass divided by the volume. And quite simply here on this one, we were given the mass at 76.31. So 76.31 grams is our mass. For the volume, well, we have a cube here, and the cube is 1.500 centimeters on each side, and we want to get that number cubed. So we're going to put 1.500 centimeters cubed. And so we're going to cube both the 1.500 and the unit of centimeters. And that is going to give us a number. So we'll go ahead and punch that into our calculator. So 76.31, and we're going to divide that by 1.500 raised to the third power. And what that will do is that will keep that number. So it will cube that number, but it won't cube the 76.31. And we're going to get 22.61. We'll have four significant figures. We have not talked about significant figures here, but after we do, you'll notice that this will make sense. So just kind of make note of that. There are four significant figures here, and it'll be our units. We always want to write the units. Grams per centimeters cubed. So 22.61. And here we'll put a nice little red box around that. All right. Next, the density of titanium metal is 4.51 grams per cubic centimeter at 25 degrees Celsius. What mass of titanium displaces 65.8 milliliters of water at 25 degrees Celsius? All right, so it's at the same temperature. That's good to know. Density can change as the temperature changes. And we're looking for mass. If we take this formula and solve it for mass, so we'll just cross multiply there, we'll get mass is equal to the density times the volume. Well, our density is 4.51 grams per centimeter, so cubic centimeter, so 4.51 grams per centimeter cubed. And our volume is in milliliters, but you may remember that a milliliter is equal to a cubic centimeter. I'm going to put a conversion factor in here. 1 cubic centimeter is equal to 1 milliliter. When we talk about dimensional analysis in the last section of this chapter, that will come into play. So after you've done the dimensional analysis, come back and look at this problem, and it will make sense. All right, and then we're going to multiply that by the 65.8 milliliters. And what we'll see here, one, is that the centimeters cubed will cancel out, and our milliliters will cancel out. And that's going to give us our answer in grams. So I just need to do 4.51 times 65.8. So 4.51 times 65.8, and that gives us 296.758. Now, we don't want to write down all those numbers. We have three significant figures here and three significant figures here. Our answer is going to have three significant figures. So I'm going to round that to that 6, but we're going to round up, so it'll be 297 grams. And that is our answer for part B. All right, so that is density. So now let's go back. And now we want to look at scientific notation. And for scientific notation, I'm going to do a special split screen here. All right, that way I can get the presentation up here and my calculator on the same page. Let me clear out that stuff. So, using scientific notation in your calculator, this is an effort to get you using your calculator correctly. And this is really, really important. If you are having any trouble doing this, you need to seek help immediately. I don't want you not getting help on this. If you can't get to campus, of course, as I record this, we're in the middle of a pandemic. If you can't get to campus, we do have online tutoring, and of course, you can check in with me in my online office hours. So here we've got 1.35 times 10 to the third, and we want to divide that by 5.00 times 10 to the negative third. So on this calculator, the this is the TI-36X Pro, which is a nice little calculator, not very expensive, which is why I like it. We can enter that in as 1.35, and then instead of hitting times 10 to the, what we can do is we can hit the EE button. And that E, when we hit the EE button, it gives us an E on the calculator. That E means 10 to the. And so here I'm just going to put 10 to the third. What's nice is that you don't have to put parentheses around this. It will treat that all as one number. We're going to divide that by 5.00 E negative 3. And then I'm going to hit enter, and you'll see we get 270,000, which is 2.70 times 10 to the 5th. So there we go, 2.70 times 10 to the 5th. And if you get something different, then you're using your calculator incorrectly, and you need help. So I've got another commonly used calculator. So I'm going to switch out my calculator just real briefly here. Switch out the calculator. This is the TI-83, and many of you have either the TI-83 or the 84. And since you have that calculator, I want to show you how to do it on this one. I don't have any of the Casio calculators, so I'm just going to do it on this one. So 1.35, and it doesn't have an EE button directly. So instead, what you need to do is you'll need to measure it as, or you'll need to put it in. The EE is the yellow button right there. So I'm going to do second EE 3, and then we'll divide that by 5.00 second EE negative 3. And that will get you 270,000 as well. So it just depends on which calculator you like to use. If you have one of the 83, 84s, they're great. Use it. Whenever you go to a testing center, that's the calculator they have there. They have the 84 Plus, really nice calculators. On the other hand, if you're looking to buy a calculator right now, order this one. I've seen this one on Amazon for like less than $20, and it does everything that the graphing calculator does except graph. So it's a real nice option. Okay, so let me switch back over to presentation mode here. And we want to look at doing uncertainty in measurements. All right, talk about uncertainty in measurements. And we'll find that there are two kinds of numbers that we will run into. And those two kinds of numbers are either exact numbers or inexact numbers. Exact numbers are numbers that we know the value exactly. And so that's going to be things that you can either count or things that are a definition value. And we will look at some of those definition values a little bit later. Inexact numbers are things that result from a measurement, and there's always some amount of uncertainty here. And with that some amount of uncertainty, we need to indicate how much uncertainty we have. And so we use different ways of writing the measurement to indicate that uncertainty. So we're going to look at a definition here that we call, or actually two definitions that we call accuracy and precision. So accuracy and precision. Accuracy refers to how close individual measurements agree with the true value. And so how close is our measurement to the true value? Whereas precision is how close individual measurements are to each other, how much they agree with each other. And so these have different meanings. They are similar in meaning because they talk about how close values are to some other number, but they have a different meaning. And so I like to use this as a demonstration of our learning objectives. All right, so for this class, I've got a list of learning objectives, and I'm going to pull up the learning objectives for Chapter 1. And you'll see that the learning objectives are listed. They're on eCampus with each section. But here we go. This is the learning objectives for Chapter 1. the way that we use the learning objectives is that I teach to the learning objectives, and so you'll see that, oh, look, hey, these are things that we've covered up to this point, right? Also for the homework, we make sure that every one of these learning objectives has at least one homework problem. And we also make sure that every one of these learning objectives has at least one test question. Furthermore, we don't have any questions on the test that aren't tied to one of these learning objectives. So we don't just put random stuff on the test that doesn't have anything to do with these learning objectives. So the learning objectives are really, really handy. And you'll see here it says differentiate between precision and accuracy in measurements. So that means you need to know what the definition of precision and accuracy are. That means there'll be at least one question, maybe even two, that show up on the test. So if it's on the learning objectives, it's on the test. All right, I like to point that out because sometimes people get into the semester and they don't even realize that those learning objectives, how useful they are. All right, again, here's an analogy over here. We've got a dartboard, and if you're really close to the true value, then you're right on the bullseye. So you're going to have good accuracy and good precision because the numbers are close to each other. If you've got really good grouping, so you throw your darts really, really well, but they're not quite accurate. So it's a little bit away from the true value, but at least they're consistent with each other. This can be a very useful number, and we don't necessarily always have to have good precision and good accuracy because we can sometimes adjust and get ourselves good accuracy that way. And then finally, we've got poor accuracy and poor precision. That's where, this is how I actually play darts. The numbers are not close to each other, and so that doesn't give us a very accurate result either. So, all right. Well, now we want to talk about the concept of significant figures. So, significant figures. We want to indicate what the number of significant figures are. All right, so the term significant figures refers to the number of meaningful digits that are written in a particular measurement. For example, if I were to give you these two measurements, on the face of it, these two measurements look like the same number. And in fact, some people would say they are exactly the same number. However, they have two different meanings. And you need to be aware of what those two different meanings are. So 2.2 grams does not mean the same thing as 2.200 grams. One of those gives us more information, and it's the one with more digits to it. So let's look at this more closely. So how are these numbers different? Well, 2.2 grams, when we write it like that, that implies that we have some uncertainty in our last digit. So it implies that there's some uncertainty in that tenths place. All right, so 2.2. So that means, it could be 2.1 or 2.3, or maybe even 2.0 or 2.4. But we know the first two for sure. We know that it's somewhere 2 point something, but we have uncertainty. We have uncertainty in this last significant figure. So uncertainty in the tenths place. Whereas the other number, with the way that it's written, it implies that there's uncertainty in the thousandths place. So we have uncertainty out here. So this could be 2.199 or 2.198 or 2.201 or 2.202. But we know these other numbers pretty well. It's just we have uncertainty in the thousandths place. Well, there's a lot more information in this number. And so when we're making measurements, we want to write down the correct number of significant figures. All the numbers that we know for sure and the one that we have uncertainty about. So when we're making measurements, we want to make sure that we write down everything that's meaningful. So for example, we're going to say, how long is this particular object? Right? So how long is this object? Now we're going to assume that the end of the object is lined up with 0. We can't tell that for sure, but we're going to assume that it's lined up with the 0. And so now we want to determine, well, where exactly, what number should we write down here? Well, clearly we can tell that this is somewhere between 11 and 12 centimeters. So we know it's 11 point something. Well, we could say more. We can say, well, the end of this object is somewhere between 11.6 and 11.7. So there's uncertainty there. It's between the 11.6 and the 11.7. So we can say 11.6 something. 11.6 something. All right. So we know that 6 for sure. We don't really have any uncertainty about that 6. All right. Well, what about the next number? So we know it's between 0.6 and 0.7. Could we estimate what that next number is? Now, usually when I'm in class, I have students estimate, and sometimes students will say, okay, 11.65. And quite honestly, I can't disagree with that. If you look at it one particular way, if you say, okay, it's the end of that black part, and that looks like it's right in the middle, so 11.65, sure. A perfectly reasonable person could look at that and say 11.65. Somebody else might say, well, it's more like 11.64. Another might say 11.62 or 11.63. I forget what I wrote. I wrote 11.63. Okay. So we do have some uncertainty in that 3. Okay. So with some uncertainty in that 3, that should be the last significant figure. Well, imagine if I came along and I put this, 11.632. Well, where did I get that 2? And in case you're wondering, where did you get that 2? I made it up. I made it up. There's no way we can write that 2 with any sort of confidence here. We already were maybe disagreeing about whether this was 11.63 or 11.64. How could we write down any extra digits? So 11.63 is really all we could do. So this is the correct number of significant figures to write down. And since there's 4 digits that we wrote down, we would say this measurement has 4 significant figures. All right. Well, now let's look at this. What about the volume? This is not a graduated cylinder. This is a burette that I measured in lab. I took a picture of this in lab. You'll see that the numbers count down. Here we've got 20, there's 21, there's 22 down there, and we want to see what is the volume. So what is the volume? Well, it's clearly between 20 and 21. So it's 20 point something. So it's 20 point something. Now, you'll see that the surface of this is curved. By the way, that curved surface we call the meniscus. We call that the meniscus. And when we're measuring where that meniscus is, we want to measure it. The best place to measure it is at the flattest part down here at the bottom, the part where we get the greatest contrast and the part where it's the most horizontal. And so we're going to pick right there where there's the greatest contrast. So if we were going to estimate, we'd say, well, where is that? What's our next digit here? So here, we can count backwards. So here's 20.5, there's 20.4, there's 20.3, and there's 20.2. Well, the bottom of that curve is somewhere between 20.2 and 20.3. So we can write 20.2 milliliters, and we know that 0.2 pretty well. Well, what about the next digit? How far, and this is where our estimate is, how far between this 0.2 and that 0.3 is it? Again, perfectly reasonable people can look at this and come up with different numbers. And that's where the uncertainty is. And so when I looked at this, I said, I'm going to call that 20.22. But again, somebody could look at that and say, no, that's more like 20.24 or 20.23. So we're just going to say 20.22. Another person might look at it and say 20.21. I guess it just depends on how you read it. But 20.22 is the number I wrote. And if I tried to write more digits, that would indicate that I am just making stuff up. I don't want you to make stuff up when you're doing measurements in lab. So the best answer here is going to be 20.22. Since there are 4 numbers there, we're going to say there are 4 significant figures in that measurement. All right. Well, next we want to look at rules for significant figures. And there are 5 rules. There's 4 if we're doing measurements, and there's an extra one if we're doing exact numbers, but it's not very hard. So for measurements, if we're going to write down a measurement and we're going to write down the correct number of sig figs, and we want to know how many sig figs are in that number, well, any non-zero numbers are significant. If the measurement is written correctly, any non-zero numbers are significant. So, for example, in this one, 375.1, there are 4 non-zero numbers there, and so we would say that there are 4 significant figures. So the 3, the 7, the 5, and the 1 are all significant. All right, here's another one, 42. Well, that's 2 significant figures. All right, so non-zero numbers are always significant. A 0 between 2 non-zero numbers, or 2 non-zero digits, is always significant. So for example, here we have 909. That 0 is significant. So the 9 and the other 9 and the 0 are significant. That's 3 significant figures. For the next one, 2.006. So the 2, the 6, and the 2 zeros in between, that would be 4 significant figures. All right, those 2 are easy. The next one is the one that always trips people up. So what I want you to do is after we go through this, I want you to rewind the video a little bit and watch it again. So, all right, our third rule is zeros to the left of the first non-zero number are never significant. So zeros to the left of the first non-zero number. So when we look at this number, our first non-zero number here, first non-zero digit, is 2. And any of those zeros to the left are never significant. So the 0.00, those are not significant zeros. So we're going to say there are only 2 significant figures here. So 2 sig figs. All right, so now let's look at this number. So our first non-zero number is 5. And so we'll see all of these zeros are not significant. So there's only 1 sig fig in that measurement. All right, so only 1 sig fig. All right, here the rule gets a little weirder. Zeros to the right of the last non-zero number are significant if there is a decimal point present. All right, so 0.000900. Well, the zeros on the left from rule 3, we already know those zeros aren't significant, but these zeros are to the right of our last non-zero number, and therefore, and there's a decimal point present, so therefore they are significant. Now, if I didn't have a decimal point, if I just had the number 900, then those would not be significant. There has to be a decimal point somewhere in the number for this rule to take effect. So 3 sig figs there, the 9 and then the 2 zeros to the right. Here we have 2.100. Well, both of those zeros, they're to the right of our last number. There is a decimal point, so those are significant. All right. One convenient thing about when you use scientific notation, if you've, whenever you write down scientific notation, all these numbers over here are going to be significant because the rules for scientific notation are that the number has to be greater than or equal to 1 and less than 10. And so any numbers that are written in scientific notation are going to be significant. The order of magnitude won't be. So here there are 3 significant figures. All right. When it comes to exact numbers are things that we get from either a definition value or by counting. All right. So some examples of things that would be either by counting or by definition value. We're going to say that these things have an infinite number of significant figures. We don't have any uncertainty. So for example, the number of people in this class. If I were to go around and count all the people who are registered for the class, it is going to be a whole number. There will be no fractional people. You're either registered or you're not. All right. So that is absolutely certain. You can count that. All right. Other things are definition values. So we would say 1 liter is 1,000 milliliters. That is a definition value. It's just a matter of fact. So that we would treat that as if it had an infinite number of sig figs. 1 mile by definition is 5,280 feet. It's a definition value. 1 gallon is 4 quarts. that's a definition value. 1 calorie is 4.184 joules. Exactly, that's a definition value. All right. So now we want to look at numbers 37 and 39. So we will look at numbers 37 and 39 on the in-class assignment here. All right, I'm going to go back to the 36X Pro here. All right, here we want, what is the number of significant figures in each of the following measured quantities? So 358 kilograms. All right. So using the rules that we just had, we want to know how many sig figs there are. Well, let's see. These are all non-zero numbers, so there are 3 significant figures. This is not a very hard problem. Not a very hard problem. So here, 0.054 seconds. Well, zeros to the left are not significant, so neither one of those are significant. So rule 3 tells us those are not, but the 5 and the 4 are definitely significant. So we'll say 2 sig figs there. Here we've got 6.3050. Well, the 0 in the middle is significant thanks to rule 2, and rule 4 tells us zeros to the right of the last non-zero number are significant if there's a decimal point present. So that means all of those digits are significant. There are 5 sig figs there. Next, we have 0.0105. Well, of course, the 0 in the middle is significant, so the 1, the 5, and that 0. These zeros to the left are not, so there are 3 sig figs there. This one happens to be in scientific notation, and with the way scientific notation works, all of those are going to be significant, so that is 5. And then finally, this one is pretty easy. There are 3 significant figures there. All right. So on this next one, it says, express the following numbers in scientific notation and round each of them to 4 significant figures. I'm going to do this in 2 steps. I'm going to move this out of the way because we don't need that. All right, so I'm going to do this in 2 steps. And when I do this in 2 steps, let's see. So we'll have 102.53070. First step, I'm going to put it in scientific notation, and then we're going to round it to 4 sig figs. You can probably do it all in one fell swoop, but I'm going to do it in 2 steps. First thing is that we want to move the decimal point just to the right of the first non-zero number. So we're going to move this over 2. So 1, 2. All right, so when we move that over 2, we're going to write that as 1.025370. And since we moved it 2 to the left, it's a number greater than 1, we're going to put times 10 to the 2. So 1.025370 times 10 to the 2. And that means 102.53070. Now, to round that to 4 sig figs, it's easy once it's in scientific notation. So we've got 1, 0, 2, and 5. For the 5, if the next number is 4 or less, we round down. If it's 5 or more, we round up. So 1.025, and then times 10 to the 2. And that is our final answer for that one. All right. Next, let's go ahead and do this one. So 6.56980. And we want to say, well, how many did we count over? Well, there is no decimal point written, but if there were, it would be right here. So the number we have to count over is 1, 2, 3, 4, 5. So times 10 to the 5th. So 6.56980 times 10 to the 5th. Now what we want to do is we want to round to 4 sig figs. So 6569. We're going to round that 9, but since the next number is an 8, we're going to round up. So that's going to be 6.570 times 10 to the 5th. Now, a common mistake there is just to call it 6.57 and be done with it, and that is not correct. If we want 4 sig figs, then we need to write 4 sig figs. All right, next on this one, I'm going to do this again. We're going to take our decimal point and go just to the right of the first non-zero number. Since this is a number less than 1, we're going to go down, or we're going to go to the right. So 1, 2, 3, 4. All right, so we had to count over 4 there. So this is going to be 2.57870 times 10 to the, and again, we counted over 4. And since we have a number less than 1, it's going to be 10 to the negative 4. So 2.57870 times 10 to the negative 4. 2578, that 8, we're going to round up. So this will become 2.579 times 10 to the negative 4. And then finally, on this one, I purposely made it a negative number and a number less than 1. We need to count over 2. So 1, 2 to get just to the right of our first non-zero number. We'll keep that negative out front. So negative 3.57202. And since we had a number less than 1, we're going to put negative, and we counted over 2. So 10 to the negative 2. And then finally, we'll round that, so 3572. That next number after the 2 is a 0, so that'll simply be negative 3.572 times 10 to the negative 2. Now, the reason that I chose this is that you treat negative numbers just like you treat positive numbers, same rounding rules, all of that. And that this negative has a different meaning than this negative. This negative tells us it's a value less than 0. Whereas this negative tells us it is a value, absolute value less than 1. So it's a fractional number. All right. We're at 52 minutes on this. So I am going to cut off this video here, and we're going to finish. This section on significant figures in the next video. And that next video should be the last video of chapter 1.